This is number 2, implicit differentiation, also involving second derivative implicitly. This is also non-calculator. We have our equation that we want to find the derivative. It's showing you what the answer is going to be, but we're going to have to go through those steps to connect that starting equation with the derivative. And if we look at this form, we see that we have y's intermixed within the equation, so we know we're going to have to involve implicit differentiation. That means every y's derivative is going to have is going to be attached with the dy dx. And then also we see xy combined together through multiplication, so there's going to be a little bit of a product rule that has to occur there as well. So we apply implicit and product rule. I notated 3x and y as the portion that is going to be applied with power rule or with product rule. So let's go through each term's derivative. Here, x squared becomes 2x. 4y squared, power rule is going to be 8y, but because we're involving y's derivative, we need to attach dy dx. 7 is a constant, so it goes 0. And then we have f prime g plus f g prime, so 3x becomes 3, g stays as y, f stays as 3x, and g prime becomes 1 dy dx. And now we have our derivative in front of us. We just have to rearrange this so that we can solve for dy dx by itself. So I cleaned this up to get it to this form. I'm going to have these two dy dx terms on the left side. So I'll subtract the 3x dy dx over. I'll move the 2x over to the right side. I can factor out the dy dx, divide both sides by the parentheses. So we have our dy dx derivative that matches our part A. Part B, show that there is a point P with x coordinate 3 at which the line tangent to the curve is horizontal. So horizontal tangent is going to occur where the numerator of dy dx equals 0. So we'll take the numerator portion, we set equal to 0, and it says with the x coordinate of 3, so we can plug 3 in for x, and we get 3y is equal to 6, so therefore y equals 2. So now we're we've now located that exact order pair. That order pair is going to be x value of 3 and y value of 2. Okay, so now we want to show that that this line tangent to the curve is the tangent is horizontal. So we're going to plug 3, 2 back into our equation and confirm that the point is on the curve. So just to, because this is from the derivative, so we're going to have to just make sure that this is a point that actually does sit on the graph. So we can let's plug 3, 2 back into the original equation just to confirm that what we're getting here is going to be consistent, is actually a point that does sit on the graph. So that means if I plug 3, 2 into both sides of my original equation, I should be able to arrive at something that is a true statement. So I can plug 3 for x, 2 in for y. We get 9 plus 16 equals 7 plus 18. And that does equal to 25 on both sides. So we know that what we found from the horizontal tangent is confirmed with actually being a point that sits on the graph. Part C, find d2y over dx2. So we're asked to find the second derivative. We'll start with the first derivative and see if we can apply the appropriate derivative rules to move our way from dy dx to the second derivative. So this expression is set up as having to go through quotient rule, numerator and denominator. So we have f prime times g minus fg prime all over g squared. So 3y minus 2x, the derivative of 3y is 3 dy dx, right? Y goes away, but y's derivative is going to result in dy dx. 2x becomes 2. The original g function stays the same, minus the original f function stays the same, and then the denominator's derivative, 8y becomes 8 dy dx, 3x becomes 3, all over my denominator squared. Okay. So we have a replacement for x and y because the order pair is 3, 2. That's the result from part B. But we also need a replacement for dy dx. We need to figure out what is the slope at 3, 2. So we can plug 3, 2 into the original, into the derivative. And we know 3, 2 produces a slope of 0. So that just means that we can replace every dy dx with 0. So all this is parts A, B, and C are connected in some way here. Replace dy dx with 0. Replace x with 3, replace y with 2, and if we clean all this up, we'll get 1 times 16 minus 9, which is 7 times negative 2, which is negative 14. And this whole thing will be 0 all over my denominator squared. 16 minus 9, which is 7, and then 7 squared is 49. So we have negative 14 over 49, which reduces to be negative 2 over 7. And this result can also tell us about whether we have a relative max or relative min. So let's think back on the second derivative test. What the second derivative test tells us is that if we have a slope of 0, which we've confirmed, and if we pair that with the second derivative value, we can determine whether that point is a relative max or relative min. So the second derivative here, we see that's obviously a negative value. So negative value is going to mean that it must be part of a concave down graph. So if the graph is concave down and a slope of 0, then the graph looks something like this, right? Concave down looks like this. The only point on the concave down graph that has a slope of 0 is this point, and we can obviously tell that point on this graph is resembling a relative max. So if a graph has a slope of 0 and concave down, that means it's relative max. Now, just to connect this with something further with second derivative test, let's say d2y over dx2 produces a positive value. Let's say d2y over dx2 is equal to 3. Let's say it's equal to 3. And the slope is 0. So if we're staring at a positive concavity of 3, then we know that this graph must be part of a concave up graph. And if we're pairing that with a place where the slope is 0, then that must be a place where there's a relative minimum. Okay. So second derivative negative means concave down, which means a relative max. Second derivative value of positive means it's concave up, and concave up means a relative minimum.